So let's go to MolView, and we're just going to close this. And then the other program that I want is ChemDL, ChemEd DL. Okay, so these are the two programs. One program will give us the rotating, but it's got to be in the library because you can't create models in this particular site. In the other one you can. So let's go to MolView. This is a structure of caffeine. What you can do here is, let me go ahead and clear this. What you can do is, of course, you can rotate the structure. Okay, so you can see the geometry around each atom. You just take your mouse and move your mouse. But let me go ahead and clear this so that I can explain to you the different features in this particular program. This right here, in organic chemistry, what happens is that if you draw a structure, okay, each end of the line and bend of the line represents a carbon. And then carbon always has 4 bonds. So if this carbon only has 1 bond towards one other carbon, it's implied there's 3 hydrogens in here. This carbon has 2 bonds to 2 other carbons, and so it's implied 2 hydrogens in here. So this particular structure that I drew is 1, 2, 3, 4, 5, 6, 7. 7 carbons long, and it's got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16 hydrogens. And if you want to see that, we can go ahead and clean up the structure. That's what the broom is for. And then take that 2-dimensional model and render it to a 3-dimensional structure. And here we have it. You notice that this is a zigzag formation. This, by the way, that I just drew is called the stick notation. This model on the right is called the ball and stick. And so you can see that we had 7 carbons, 1, 2, 3, 4, 5, 6, 7, and each hydrogen, the hydrogens are put in there automatically. And we do that in chemistry because we are lazy to write detailed structure. It requires the audience to know how to interpret these structure. So this right here happens to be heptane. That's the structure of heptane. Okay, so again, you can see that that's basically it. If I extend this, let me just draw a bunch of carbons coming out. I don't have to put in the carbons, it's implied, and then render that. You can see that that's exactly what's going on. Okay, I've added, and just do 1, and then here it is. Okay, remember that there are 1, 2, 3, 4, 5, 6, 7 carbons in this structure. Each carbon here has 2 bonds, so that means there are 2 hydrogens. I can do a cube like that and then get a 2-dimensional model. Okay, I can do a alternating double bond, which is our benzene ring, and do that. See, now this carbon has 1, 2, 3 bonds, so that means the 4th is a hydrogen. Belongs to this carbon, 1, 2, 3 bonds. The 4th is an implied hydrogen. Now, these features right here, the trash means to trash your structure. The erase means that I'm going to erase a bond, maybe. Let me do this. Okay, so let me go ahead and fix that. And let's say I want to remove one of this because I made a mistake, so I can erase it, and then I can replace maybe this with an oxygen, and then get the 2-dimensional structure like that. These are wedges and dash to give you some sort of 3-dimensional perspective. So if I put a line right here, and then I put a wedge here, and then a dash here, and then another line here. It tells me that I have basically a three-dimensional. The wedge comes out of the plane of your screen. The dash means it's going behind the plane of the screen, and lines represents the same plane as the screen. So let me go ahead and render that. And that's what we have right here. Okay, you see how we have a this thing is called a tert-butyl group. This thing right here, it's called a tert-butyl group. So that's basically the templates that you have here. You can put electrons or you can remove electrons. So let's say that I put electrons right here, then that'll give it a charge. I can also remove electrons. Let's say I remove an electron here. Okay, so I can do that. And then, let me clear this. These are the different atoms. The more frequently used atoms are shown right here, and that's because this program is made for organic chemistry. And then if you want more elements, then you click on that and it will give you the periodic table. So one of the chemicals that I made in graduate school had 2 iridiums and chlorine. Let's see if this works. And then let's see if I can't put a carbon in here. Actually, let's do a ring, and then I'll put a nitrogen in one of these. Okay, and another ring, and then a nitrogen on one of these. So this is a structure. Let's clean it up and then create the 3D model. Here it is right here. Okay, so that is how you would use this program, and it gives you a pretty good realistic view. I can change the different view to ball and stick, or just a stick, I mean. I can do a van der Waals radius, and that tells you the size of these things. I can do the wireframe, or I can do the lines. I can change the background here to gray. I can change it to white. Okay, I'll go ahead and go back to my ball and stick and then make the background black. That way I have some contrast. And then these other tools here, you could probably get some spectroscopy information. We'll try that in some of the compound that we have. So it's got some advanced features here. So let me go ahead and do our structure. Okay, I'm going to clean this up. The first chemical is difluoromethane. So it's got a carbon in the center, and then it's got fluorines attached to it, and then I'm not even going to do the hydrogens because hydrogens are always implied. I am going to connect these. Okay, you notice that sometimes the carbon is shown, sometimes the carbon isn't. I'm going to clean it up, and then I'm going to render it. So that right there is difluoromethane. I'm going to go ahead and cut and paste this so I can put it in my worksheet. So I'm going to give it a white background, and then I'm going to copy and paste. Okay, it's on my desktop. I'm going to go to ChemEd DL, and then I'm going to put in here difluoromethane. And it actually is in the library, and if I click on that, it'll find it. And here's the structure right here. I can rotate it with my mouse. I can make the molecule spin. I can do the van der Waals radius, which tells me the size of these things. I can actually do the bond length. Okay, I can also do the bond angle, and you can see that this is nearly almost a tetrahedral. 109.5, not quite. I can label the atoms for more complicated chemicals. Okay, I can do partial charges. Later on in Chem 200, you're going to learn about formal charges. That's what it is. I can turn off the labels. I can do molecular dipole, and that's what we want. We can see that this particular chemical is polar because it has a dipole moment. And I can also do the dipole for each bond. You can see that fluorine is more electronegative, so there's a dipole pointing towards the fluorine, a dipole pointing towards the fluorine, and so these are the other dipole. And then when you add up all those vectors, you get the molecular dipole. So I'm going to write 1.1719 in my sheet here. 1.1719. Up. Acetic acid has carbon, carbon, oxygen, oxygen. Remember that hydrogens are implied. I am going to connect these. Yeah, erase that. That was an error. And I'm just going to put the double bond right there. And I actually need to show that it's a double bond. And you can see that that's the structure I have. But when I clean it up, it does that. That right there is acetic acid. And if we do the three-dimensional structure, we have this. And that's acetic acid. So I'm going to copy and paste this structure into my notes. You can see it's tetrahedral on the carbon, it's trigonoplanar on the second carbon, and it's bent on that oxygen, just like we predicted. Okay, it's bent on that oxygen because there are lone pairs on this oxygen. When you do the model, it doesn't show the lone pairs. Let's go ahead and put acetic acid up here. And you probably already know that acetic acid is polar. Here it is. And we can go here and figure out what the dipole is. The dipole for this guy is only 1.5783 dBis. That's the unit. 1.5783.